Our next speakers are Jonathan and João. I've forgotten what order you're going in, but they're talking to us about something very intriguing called the Meerkat vision.
Thank you. So we're going to talk about Meerkat, which is a vision for a future in which we can build reactive web applications and have first-class language support that provides live updates and scales to the kinds of apps we build today. And this is a collaboration between João and myself. So my personal motivation for this was building an app called Noteful. Noteful is a free app that teaches music notation and theory. You can check it out on the app stores or noteful.net. But what I learned as part of building this app is how do we build apps these days, right? And a big part of it is something that originated as functional reactive programming, right? In fact, Noteful is a packaged up web app. You can run on your phone. It uses the Angular reactive programming framework. And the benefit of reactive programming is essentially declarative UI programming. You describe in a declarative way how pages in your UI are constructed given the data in your system. And when the app data changes, the framework detects this and the pages are automatically updated. So it's super cool. It gets rid of a lot of the kind of hand-munging updates from the UI to get to the UI from your data. But all is not right in paradise. Okay, so in industrial reactive programming, you can connect data on the client with the UI. But in fact, in most modern web apps and mobile apps, data is actually on the server, right? And access to the server is not usually by a reactive query. It's by an old-fashioned, non-reactive query to the server of the database, like pulling new data. And so this creates an impedance mismatch, and the programmer is forced to solve it, right? The programmer must keep client-side and server-side stay consistent, which is a source of lots of complexity and lots of bugs, and I've experienced these myself. So, furthermore, reactive programming frameworks really give you this update of data automatically, but code updates are still hard, right? And in fact, they're highly error-prone. You have to do this dance where you update the database schema, and then you update the data in the database to match the new schema, and then you update the server, and finally you can update the client. But by the way, if you get any of this order wrong, or you're not backwards compatible, because the clients aren't going to be updated immediately, this goes wrong, right? And your users see the pain. So there was this awesome work from actually 9 years ago by João Costa Seco and his student for a way to do this much better, a live reactive programming model. And João will give a demo of what they've been working on.
So let me show you what we had 9 years ago. And so we had 3 simple constructions to define a web application. So we could define a variable. That is the symbol here for a database table, something on a server. Okay, let me change to my IDE, so quite simple. And so if we paste here the command, and here every time, this is a live demo, so it needs to take a while, right? Oh wait. What happened? Shall we switch to the backup?
We just tested this. We can switch to the backup if...
So...
Yeah, try it one more time.
No, it doesn't. It lost the connection. Okay. That's not good. Yes,
there you go. You see the issues.
Plenty of issues. Okay, maybe we can switch to the backup. And the backup are some slides that we have stored at the end of the presentation. Here, right? So the idea is to have, well, now I need a pointer. The idea is to have some language to define the state of the application. Okay, so we just say var minutes equals 0, and then something to define the logic of the application. And you can say, okay, now I define a name called seconds, and it's minutes times 60. Okay. And the third ingredient is, okay, we have state, we have logic. How do we change the state? And we define simply a data type, which is actions, and actions contain assignments. Okay, in this case, increments minutes. Of course, we can define a few more names, and using an HTML-ish part of the language, we can define a user interface. And what you get is here, what you would get if the thing worked. Okay, so what happens is that if you immediately use the button, you get 60 seconds. Okay, you can keep on using it. Behind the scenes, what happens is that you have state, and then you have two definitions depending on that state, and that reactively update whenever the state is updated. And then, of course, you have UI over there, which is just another value of the language. Okay, so whenever you tick, then the state is updated and everything is propagated immediately. Okay, we can then keep on going and defining new functionality by having a new definition. So now we want to reset the minutes, but we want to add that to the UI. So by redefining the definition called buttons over there, by redefining the whole definition, immediately all the clients that were using this definition are updated not only with data, but also with code. So a button appears in everybody's user interface because it's been updated in the code base. So of course, what happened now is that we redefine the buttons, and the pages, all the pages are updated. The third step that we want to do is, okay, it's a bit dumb to be counting minutes, right? What we want to count is seconds, and then show minutes. So we can now redefine seconds from being a definition based on minutes, and say, okay, no, seconds should be a variable, so the state should be storing seconds, and the current value is minutes times 60. Okay, then we probably should redefine the increment action and the reset action to, instead of changing minutes, to be changing seconds now. And not to lose any of the definitions before, we change the minutes, which were the state, to a view of the seconds. Okay, and then there's a detail here, is that we want to do this in one go, because this system lets you update code and data concurrently. So, well, it sequentializes everything so that everything goes well. But if you do these 4 things in a row, you may lose data because someone may increment the minutes variable that was no longer in use in between these instructions here. Okay, so your interface looks the same, the behavior is the same, but the state beneath is different, completely different. So, and we do this in an atomic block. So yeah, you are still counting minutes, but underneath you're counting seconds. Okay, so and this is, so we switched from minutes being the state for seconds to being the state. But yeah, we need to count seconds. So to count seconds, well, we define a new function, a new definition that increments the seconds, and we add that, not to lose the tick button that counts minutes. Now we have a small tick. And what happens now is that whenever you call small tick, you count seconds and not minutes. And that's, well, the same dependency graph is used in order to propagate the data changes from the increment seconds over here, and the change seconds. It also changes minutes, not used anymore, but then propagates to your user interface, the proper changes. Okay, and that was the demo that I wanted to do live. Didn't work, sorry. But so let's go back to this. Get back to Jonathan.
All right, so this is a super cool programming model from my point of view. It provides some fundamental constructs for building reactive multi-tier systems, such as the state variables that you saw. We also have tables, pure computation that computes interfaces from those, and of course, any state changes are propagated along the dependency graph to the UI. Furthermore, it's reconfiguration of state and code, and it's all type checked, so you know that your live reconfigurations won't break anything, at least as far as the type system of the programming language. There's more features like making sure there's no cycles and dependency graphs, so that propagation stays finite, and we have glitch freedom, which makes sure that you don't see kind of artifacts from variables being updated in the wrong order. However, there are also some limitations, right? At this point, it's a programming model, one that sometimes doesn't work, right? It's not an industrial scale framework. But a bigger issue is that the semantics are really for one centralized system. Because there's only one server, it's not scalable to large amounts of data, large numbers of clients. It's not scalable to large organizations where you might really care about modularity of implementing different services. And there's a sequential queue of execute and update operations, which actually gives us some very nice properties, but also limits scalability because we can't do anything concurrently. So fixing this requires some programming language ideas, right? Modularity, some distributed system ideas, availability and consistency, ways of synchronizing truly distributed updates, as well as extensions to things like the data model, providing the ability for disconnected operation in case the Wi-Fi comes down, right? Maybe the demo can still work. And software lifecycle, we'd like to provide more software lifecycle support and interoperation from a software engineering point of view. So we've expanded this initial prototype into a vision for a future that we call Meerkat, after the colony of little animals that work together to do great things. And our goals here are to support linguistic reactive programming, right? Where you have this nice model of computing interface from data and updating the interface when the data changes. But we want to make the reactivity go across the whole stack, where the stack can be, not just one server machine, but a whole network in the cloud and on your local device. And so we have this notion of services, which are, can be in the cloud or on your local device. They can be replicated. They can be sharded for scalability. They can be on your local device so that we can support disconnected operation and local first software. Maybe these, you need to customize the kinds of semantics these services provide in terms of consistency guarantees, for example, or provide more interesting kinds of data models than what we support right now. And of course, we'd like to make these live code updates distributed and provide some DevOps support of the kind that you see in software engineering research, but with some nicer semantics because we control the programming language. So let's talk a little bit about what these mean. Linguistic reactivity. We want a bird's eye declarative view of the system architecture for programmers. This really enables a lot of later goals. The ability to control custom semantics from one place, the ability to do synchronized and type-checked live updates, to provide more DevOps insight than you can in a system with a lot of layers and frameworks. Across the software stack, we want the UI to react to server data store updates without requiring the programmer to write any glue code, right? In João's demo, the UI definitions just reference the data, right, on the server. We also think it's useful to really have a data store that's conceptually imperative actually be imperative, right? I love the model of Elm for programmers, but I don't necessarily love the fact that the data model is a stream of functional values, right? It actually makes expressing things more complicated in my opinion. There's some examples in the paper that go into that. But we want type checking, right? We want to assure consistency across clients and servers, things like data formats and operation signatures. We want termination checks, as mentioned already, in the live updates. There are some reactive frameworks that kind of move in this direction, like Meteor and Rescala, but we believe there's really value in having a language here, right? A framework can't give you as close a match to the user's conceptual model as a language can. Some boilerplate still is necessary to connect the client to the server. See the paper for details. And of course, in a framework solution, we lose some of these benefits of type checking and certainly safe live updates. So what's the key to making this attractive model really scale? So we believe the key idea is that of a service. In our model, a service is a modular unit of development, of composition, of deployment, and of updates. It's analogous to microservices in modern distributed system architectures. So we want to define services using the kinds of constructs João demoed. We want to have signatures that can export definitions and actions, but perhaps hide internal state like variables and tables at your option. We want services to compose, just like one microservice can use another. Imports can be specified by signatures and URLs, or you can make them dynamic using a kind of functor-like construct that allows dynamic binding between these things. We wanted to provide the ability for these services to be developed and deployed independently, either by different organizations within a company, or maybe even different organizations working together as peers. And live updates, now they can be scoped to a service and not affect the outside world, or they can go across services and allow several services to be coordinated and updated together. Location is important, right, in distributed systems. And there's a new paradigm called local first software that really emphasizes users' choice and how their private data is managed. And to support this, we want Meerkat services and data to be locatable, right? So you can put things on the user's device to support disconnected operation or privacy. You can replicate it to make access anywhere. It's what you want. And in the longer term, we'd like to explore ideas like inferring data and code location kind of within this system, because again, we control the distribution, so we can use confidentiality specifications, size of data, device capability, sharing between users as a way of directing this. We'd like to, we know that one size does not fit all for distributed systems. So with Meerkat, we're looking at providing a default level of causal consistency. We're choosing causal because it's basically the greatest consistency you can have that's available to sub-partitions and has fairly good scalability characteristics. There's no global coordination necessary. But we also want to provide an option and support, explicit support in the language for eventual consistency, for greater scalability for those who need it. And of course, standard ideas like replication for reliability or sharding for other dimensions of scalability in data. So we want to provide some great defaults that we think a lot of people will use. And I think it's a story of programming languages that if you provide a few really good things, people can use the tool effectively. But again, two sizes also don't fit all, right? So we'd also like the ability for people to plug in their own database, maybe a commercial database that's reactive, and definitions become select queries, actions become insert updates. And then looking at more interesting data models that we don't support right now, like referential integrity, for example. Just to give you a little bit of technical material on how we're thinking about some of these issues, I wanted to give a little advertisement for Historiographer. This is by Julia Freeman and Timothy João, who actually presented a poster in the student research competition last year and won. So Historiographer gives you causal consistency and glitch freedom. To give you a little bit of an idea of what this is, consider this example. We got 3 variables, 2 definitions that depend on them, and 3 different actions. What the actions are going to do is to make sure there's no interference, they'll acquire read and write locks on the variables that they affect, right? And so actions 1 and 2, they both access variable y, and so they'll be mutually exclusive. They cannot interfere. So for causal consistency, we want to track and honor the history of updates. And so if action 1 locks this variable y first, then before action 2, for example, then this definition S here, right, will see the update from action 1 before it sees the update from action 2. So that's causal consistency. Furthermore, action 1 is going to update both x and y, and those are both going to affect definition S. But we want those updates to arrive together, right? Because otherwise you're going to see values of the definition S that don't correspond to any possible x and y, right? And so that's what's called glitch freedom in the literature on reactive systems. But just to give you one more example, action 3 here touches some different variable z, right? And that's okay. Action 3 can run completely independently of action 1 and 2. But because we have causal consistency and not serializability, these definitions might see the updates from action 2 and action 3 in different orders. And that's the price we pay for not having global synchronization, right? If you want global synchronization, use our plugin, add a database. So the final thing we want to look at is distributed live updates and developer operations. So we want to extend historiographer, which the initial prototype was just about data. We want to support code updates, including non-monotonic code updates that can break existing code. This gives us maximum flexibility, but it will require some locking and delays. And of course, if some devices are disconnected, they can't be updated, right? And so we're going to have mechanisms for handling exceptions that might be related to asynchronous code updates. We also want to look at staying completely monotonic. So this is a pretty common strategy used today, but we can provide some key new advantages. So when you deploy a new service, we can check that it doesn't break anything in existing services. I think the tierless view, the type checking, the atomic deployments make everything easier compared to today's infrastructure where these operations are typically pretty challenging and sometimes slow. And then we want to provide DevOps support to give developers a great experience, right? So, imagine preparing an update because these are declarative and updates in code, we can replay them sequentially in deployment, test, and production in exactly the same way. And it's all type checked and safe. Furthermore, I think having control of the distributed system gives us the ability to do visualization and debugging that can give people a lot of help in addressing issues with the programs that they write. So we are working on building this right now. Our first goal is to take the prototype that you saw and make everything distributed, right? So we have distributed modular services with safe live updates and causal consistency. And we want to make it fast. We know people care about performance. So we'd like, since we're going for causal consistency, we'd like to demonstrate scalability beyond what you can get in a sequentially consistent relational database. We're compiling to Rust and HydroFlow, which is a state-of-the-art research infrastructure for distributed systems. We'd like to be competitive with, maybe not exactly as fast as native HydroFlow applications, and then we'll go from there with some of the other vision directions. I want to acknowledge that we're building on a ton of related work, some of which I've already mentioned, others of which is on this slide. There's a lot of cool work in this space, and we just want to bring it together in a framework that will, in a language that will help people, write web apps more easily. So that's Meerkat, scalable reactive programming with live updates. Here's a reminder of our vision, and we'd love to have questions, discussion, comments on the ideas.
Very much. We have time for one or two quick questions, but I'm going to ask our next speakers to get set up while that happens.
Hi, Jonathan. Great. I love your vision. I just have a sort of a technical question for you, which is that, in my experience, in general, schema change in a distributed context has to be bidirectional. So when you converted seconds to minutes, there's still code out there that wants to do an increment minutes. And somewhere there's going to have to be something that converts that increment minutes to add 60 to seconds. And I didn't see that in your solution. Have you thought about that, and do you have a solution?
Yeah, it's a great question. So I think the modularity of services and the information hiding of actually giving these interfaces is an attempt to do that. While you can, make you can just put variables out there, which will make your system fragile if you want to. We imagine the best practice, as in object-oriented programming, will be to hide, literal variables and tables behind things that are more abstract, like update actions and definitions. And so then the idea is that you can you can replace those definitions with ones that work against the new schema in a way that's seamless to clients. And we can check that because it's all type checked.
Okay. Thanks. Great work.
Okay, last call for questions. Otherwise, let's thank Jonathan and João again.